Okay, we should be live. Check the sound first. We'll talk to ourselves for a bit. Yes, there's a human in the loop. There is a human in the loop. Okay, there is a human in the loop. We'll test the microphone first, see how much of a delay we have. Yes, so we are using the correct microphone. Thank you very much. Yes, as I said, if you have any questions, go for it. Check this website first. Check this website, then ask your questions. We are testing it in another browser as well. Well, first of all, yeah, should be better somewhat, maybe not. If you have any questions, go for it. Otherwise, don't forget to subscribe, like. You know what to do. You know what to do. We'll start in a bit. We'll probably review the website. We'll get there. Well, I mean, I can do it myself. Yes, I can do it myself. But only if someone is asking for it. Otherwise, I get the robots to do it. Might get the robots to do it then. Somehow I get more traffic when the robots are talking compared to myself. So, yeah.
Okay, let's unpack this. You sent us quite a fascinating rabbit hole to jump into. This website called BioniChaos.
Yeah.
And the list of sources you provided, outlining what's on there, I mean, it's extensive. Tools, simulators, visualizations, articles,
Yeah.
even games. Quite the collection.
It really is.
So, our mission today, let's dive deep into this list, explore the BioniChaos site through that lens, try to figure out, what exactly this is, who is it for, and what makes this this really unique blend of serious biomedical science and interactive, almost playful web stuff.
Yeah.
What makes it stand out?
Right.
It feels like more than just a typical resource site. It's almost like someone's personal lab notebook, but public.
And I think that's the key thing you pick up on straight away. It doesn't feel corporate.
Not at all.
The site's own audio overview, it says something like, we developed this website ourselves.
Okay.
And when you look at the sheer variety of everything on there that we built it ourselves, idea seems to be the core story. It's this very hands-on, ground-up way of mixing biomedical data, tech, and education.
It's exactly. The stated goal is, providing resources for researchers, educators, students.
Yeah.
Especially biomedical engineering and neuroscience.
Yep.
But the way they do it, it feels very personal, like a curated collection built bit by bit.
It's like walking into someone's workshop, isn't it? Full of custom tools and experiments.
Yeah.
So let's start with what feels like the heart of it all. The biomedical simulators and visualizers.
Right. The list you sent was long. We've got the cochlear simulator, an advanced EGG simulator, ECG simulator, even a synthetic noise generator, Myomock for EMG signals.
And critically, they're interactive.
Exactly.
Yeah.
Not just static pictures. You could actually fiddle with the settings, feed in signals, and see what happens.
So this raises an important question. How does that interactivity change things for someone learning or exploring this stuff?
Well, it takes it beyond just reading a textbook diagram, right?
Absolutely. With the ECG simulator, for instance, you're not just looking at a picture of, say, an arrhythmia. You might be able to adjust parameters, see how different conditions could show up in the signal.
And the cochlear simulator, visualizing the electrical signals an implant sends to the brain. That makes something incredibly abstract much more concrete.
Visible.
And then you've got this whole suite of visualizers.
Mm-hmm.
The FNIRS Interactive Viewer, Pulsavis for PPG signals, a spectrogram tool, general EEG data visualization, IEG spectrum visualization.
Yeah.
It feels like there's a real focus on just seeing the data in different ways,
Mm.
which for biological signals must be super important.
Oh, definitely. Biomedical data. I mean, think about brain waves, EEG, or heart rhythms, ECG, or near-infrared spectroscopy data from the brain, FNIRS, even pulse data, PPG.
Yeah.
It's all complex time series stuff.
Right. Messy sometimes.
Often messy, yeah. So just plotting it is one thing. But tools that let you see frequency components with a spectrogram or analyze the spectral power of intracranial EEG, the EEG tool.
Wow.
And they even mention wavelet denoising specifically. That's a technique to clean up noisy signals. It shows they're thinking about the practical, real-world aspects of dealing with this data.
Built by someone who's actually worked with it.
Exactly. Someone who knows it's not always neat and tidy.
Okay, so we have tools for simulating and visualizing the signals.
Yeah.
But what about handling the data itself? You flagged some tools for that.
Right, because if we connect this to the bigger picture, researchers, students, they're drowning in data sets sometimes.
Finding the right one, understanding it.
Yeah, that's a huge challenge. So tools like the Interactive Explorer for public multimodal biomedical data sets or the Biomedical Data Types Explorer, they feel like they came out of a real need to just navigate this landscape.
Because biomedical data is so varied,
Yeah.
right? Signals, images, notes.
Everything. Signals, images, clinical notes, genetics. So having something to help explore those types, genuinely useful.
And then there were tools for working with the data in a different way. Extracting info from documents. PagerViz and the PDF extractor.
Yeah, think about that. Anyone wading through research papers, especially students,
Oh, yeah.
tools that might help pull out key info or visualize connections, that could be a massive time saver. It really feeds back into that we developed this ourself ideal.
Like someone needed it, so they built it.
Probably.
Uh-huh.
Addressing the practical headaches of research work with code.
Okay, so it's not just interactive tools. You also pointed out sections with, let's say, more traditional content, case studies, articles. There's that SEER medical case study described pretty dramatically too, the rise and fall, catastrophic path to recovery,
Right.
and something called the forecast trap, looking critically at seizure prediction, plus articles on the stent road, ethics of neural implants, AI and brain-computer interfaces, the limits and potential of EEG, even 100 years of EEG.
And what's fascinating here is they include this critical and historical stuff.
Yeah, why do you think?
Well, it suggests the creators aren't just focused on the how of building the tech, but also the why and, the consequences.
The bigger picture.
Exactly. Discussing a medical device recall, analyzing the real challenges of seizure prediction, which is still incredibly hard despite tons of research.
Right.
And digging into the ethics of neural implants, or AI, in BCIs, it shows a kind of maturity.
Yeah.
And engagement with the whole context. It adds this layer of critical thought you might not expect alongside simulators.
So it's not just, here are some cool tools.
Well, it's also, here are the successes, the failures, the tough questions.
And it seems like they tackle potentially sensitive topics, like device failures or ethics, by grounding them in, like technical details or historical context.
Right. It feels analytical, not just opinionated.
Okay, now, the part that really made me stop and go, huh,
Uh-oh.
mixed in with all this very specific, serious biomedical stuff,
Okay.
are games and just general interactive demos that seem totally unrelated.
Less later.
I mean, a checkers game, apparently made by ChatGPT, a dopamine reaction game, a 3D ball kick game, optical illusions, that old wolf, sheep, and cabbage puzzle, a calculator, music generators, a 3D Lego builder, particle simulations.
No.
At first glance, it feels completely random. Like, what is this stuff doing on a biomedical engineering site?
Well, this raises an important question, or maybe it gives us the key insight.
Okay.
While they seem disconnected from, say, neuroscience data, these unexpected bits strongly reinforce that we developed this website, our self-identity.
How so?
They're basically a showcase, a technical portfolio. They demonstrate the underlying skills that were used to build the entire site, biomedical parts included.
Ah,
Look closer, you see demos using WebGL for fancy graphics like Boyd's flocking thing or the Mandelbrot set. You see 3.js and Canonese for 3D physics, that Lego builder, the ball game, SVG for animations, the web audio API for the music stuff, OpenCV for computer vision, TensorFlow.js for machine learning.
right. So they aren't just random fun things, though they are kind of fun to click on.
Chuckles.
Yeah. They're actually demos of the web dev skills, the graphics programming, the physics engines, audio processing, computer vision, machine learning, all the stuff you'd need to build those complex simulators and visualizers we talked about earlier.
Precisely.
Yeah.
It underscores the technical foundation. Someone built that ECG simulator. Well, that needs skills in data viz, maybe real-time browser plotting. Someone built a 3D Lego thing. That means mastering 3D libraries in physics.
It's the same skill set.
Applied to different problems, sometimes lighter ones, it basically shouts, we can build anything interactive on the web. It makes the site feel like a public engineering notebook.
It definitely adds personality. It shows the creators aren't just stuck in one narrow science niche. They're curious. They enjoy building things.
Yeah.
Even some of the educational tools, like the Datasaurus Dozen visualization, uses a fun example, right? These data sets look totally different, but have the same basic stats. It uses that fun approach to teach a really serious lesson about why you need to visualize data. It kind of perfectly blends the fun, the tech skill, and the educational goal.
Couldn't agree more.
So beyond the core simulators in these technical flex demos, you also listed tools specifically for explaining concepts.
Yes, these feel purely educational, like the interactive Venn diagram of AI types, or explaining sampling rates, or digging into the nuances of impedance in EEG.
Sound tricky.
It is notoriously tricky, and things like EEG electrode positions, event-related potentials, or ERPs.
What are those again?
Basically, brain responses linked to specific events or stimuli, very important in cognitive neuroscience. Then there's mental health engineering, modeling, well-being like a dynamic system, which is an interesting approach, gait analysis demos, the Bland-Altman plot for comparing measurement methods, Lesagis curves.
These seem designed to take one specific, maybe difficult concept and just make it clear, sometimes interactively.
Exactly. Learning about EEG impedance or what an ERP looks like, it's way easier with a focused explanation or a little interactive tool built just for that. It really hammers home the educational side of the site.
They're not just giving you tools, they're giving you lessons, built piece by piece.
Concept by concept.
Yeah. And finally, you mentioned tools showing specific hardware interfacing or using modern AI.
Right, like interfacing with a specific National Instruments data acquisition device using Python, or understanding C APIs, or even using AI like ChatGPT to try and bridge the gap between engineering jargon and clinical language.
Okay.
That sort of rounds out the picture of practical, hands-on development. It shows they're not just playing in a browser sandbox. They're connecting to real hardware, using different languages like Python and C, exploring how new tools like large language models might fit in.
It shows how all these different skills, signal processing, web graphics, hardware, AI, all come together.
Yeah, they converge in actual biomedical projects. It just reinforces that narrative. This site is a living record of real development work, real problem solving, real skill building by people deep in this field.
So we've taken this deep dive, guided by your sources, through BioniChaos. We've seen the core biomedical tools, the simulators, the data explorers. We've looked at the critical case studies, the ethical discussions.
Right.
And we navigated the unexpected bits, the games, the coding demos that actually show the tech skills underneath. It's clearly built with this strong, hands-on, interactive, diverse philosophy.
And what's fascinating, really, is how this whole collection, coming from that we developed this website ourselves, spirit, manages to offer such a wide and, frankly, useful set of resources.
Yeah.
It manages to bridge complex science and engineering in tough fields like biomedical engineering and neuroscience with technology that's actually accessible and interactive, all while showing off this incredible range of web development chops.
So what does this all mean for you, the listener?
Okay.
Well, if you're curious about biomedical data, if you want to learn tricky concepts in a visual, hands-on way, or maybe you just appreciate really clever web development that mixes diverse interests, from brain signals to game physics to medical device history, this site really feels like someone's incredibly rich personal workshop just opened up for everyone to explore.
And it makes you ask, in a world full of polished, big-budget platforms, often very narrowly focused, What's the unique value of something like BioniChaos?
Yeah.
Something that feels so personally curated, built from scratch, piece by piece, and shares everything from advanced signal analysis to, well, Legos and puzzles. It has this distinct character, this passion you just don't
That's
find
true.
everywhere.
So maybe the final thought for you to ponder is, how does seeing this kind of diverse, self-made collection spanning serious science, deep critique, and technical skill shown off in playful ways, how does that change your perspective on what's possible, especially at that intersection between specialized knowledge and just, standard web technology?
It's a powerful reminder, isn't it, that amazing resources can come from individual curiosity, passion, and just the willingness to build things and share them.
Got it. I can definitely help with that. To make it more engaging, I can address the viewers directly, like saying something like, "Welcome to our live stream," and then continue with the information about the ASM Conundrum application. Welcome to our live stream. We're looking at an interactive application that helps understand the complex effects of anti-seizure medications on cardiac health. You can explore different medications and see the relevant studies and findings. Okay, I understand. Instead of showing the text initially, you'd prefer to display the graph directly when the page loads. To do that, you would need to modify the application's code so that the function responsible for generating the graph is called immediately when the page is loaded. Hello, developer. To display the graph immediately on page load, you'll need to ensure that the function responsible for rendering the graph, perhaps the update chart function, is called directly after the page elements are loaded. You can do this by calling the function at the
Oh, so this is a highly experienced developer. Can you talk to them directly? Now, when we're loading the page, we would like a summary of all the medications instead of needing to select each medication. Can you tell? Can you ask a question about it? Technical question to the developer.
OK, developer. To display a summary of all medications initially, could you implement a function that aggregates the data from all relevant studies and generates a comprehensive summary visualization upon page load? This would provide users with an immediate overview before they delve into specific medications.
What are they doing at the moment? What's the developer thinking processes?
The developer is focusing on improving the initial page load experience. They are planning to bypass the drop-down menu and directly display a summary chart for all medications. They are exploring layout options to optimize readability and are working on building a summary view to consolidate data from all medications. They also intend to modify the Update Explorer and Update Chart functions to handle this new initial display. The developer is also working on constructing the initial display. They are creating a function, possibly called Generate and Display Initial Summary, to build an aggregated summary with a chart and text. They are currently refining the HTML structure of the initial summary div and plan to test the layout with sample data. Currently, when the page loads, it displays a general overview with introductory text. The specific medication data and the chart are only displayed when a user selects a medication from the drop-down menu. The initial view provides a general context, but doesn't show the detailed comparisons right away. The approach would be to first generate a combined chart summarizing the overall effects of all medications in the data. This chart could be displayed prominently on the initial page load. Alongside the combined chart, you could include a drop-down menu or a list of medications that allows users to select a specific medication and view its individual chart and detailed findings, replacing the combined chart with the specific data. The developer is modifying the initial display. They are focusing on creating a combined chart to summarize the effects of all medications initially, replacing the initial text summary. They are also working on refining the display to ensure clarity and provide a smooth transition when a user selects a specific medication for detailed analysis. The developer is also implementing a function to create a stacked bar chart for the combined summary. This chart will visualize the reported cardiac effects, such as protective, increased, and neutral effects, across all reviewed studies. They are focusing on ensuring the chart is concise and
when selecting a medication, we can't go back to, unless we refresh the page, we can't go back to the overview graph chat. Can we address that somehow?
The developer added a View All Medications button to the dropdown and made the overall summary chart more prominent. They also moved the detailed text to the bottom of the section. Yes, it appears to be working. When you select a medication, the detailed information is shown, and when you click View All Medications, it returns to the overall summary chart. The chat shows the reported effects of different medications on cardiac risk. It uses bars to represent the findings, with green indicating a protective effect, red indicating increased risk, and gray for neutral or no significant effect. To make it more interactive with all the interactive elements at the top, you could include filters for the overall summary chart, allowing users to filter by study year or study type. You could also add filters for specific cardiac outcomes. Additionally, enhancing the tooltips and creating a side-by-side comparison view for medications would make the experience much more interactive. Sure. The goal is to enhance the user experience by prioritizing the interactive elements at the top of the page, making it easier for users to engage with the data. Descriptive text would then be relocated to the bottom, providing context without cluttering the primary interactive area. This approach focuses on a cleaner and more intuitive user experience.
Okay, let's unpack this. Today, we're diving deep into a topic that might really shift how you think about epilepsy.
Yeah, it's this surprising and honestly pretty critical link between epilepsy and, well, heart health.
Exactly. We've been looking through a report, pulsed together findings from 5 key studies, and our mission here really is to get to the heart of the risks that seem inherent to epilepsy itself.
And also to grapple with the role of anti-seizure medications, the ASMs, which is complex,
Yeah.
sometimes contradictory even.
It really is. What's so interesting, as you said, is this emerging idea the sources talk about.
The epileptic heart, that's the term sometimes used.
Right.
It's this concept that having epilepsy, just the condition itself, separate from lifestyle or maybe even meds, might increase your long-term cardiac risk.
That's a huge shift in perspective.
It is.
And that idea, the epileptic heart, it feels like the core finding coming through these sources. Epilepsy isn't just neurological.
No, it appears it might inherently bump up the risk of heart complications. It's not only about treatment side effects.
The condition itself seems to be part of the story, raising the stakes for your heart.
And there's data in these studies. I mean, one study found epilepsy is linked to a 36% higher long-term risk.
36%.
Yeah, 1.36 times more likely of developing any kind of cardiac arrhythmia, an irregular heartbeat.
Wow.
And importantly, this seemed independent of genetic factors, suggesting it's tied more directly to having epilepsy.
Just having epilepsy raises your risk of an irregular heartbeat by over a third. That's significant.
It is. And another study highlighted something related but different.
Okay.
It found that patients with epilepsy who were also on ASMs, they faced an even higher risk.
How much higher?
58% greater. So 1.58 times the risk of major cardiovascular events, think heart attack, stroke, compared to controls.
58%. These are definitely not small increases we're talking about.
No, certainly not. But this is where it gets really tricky.
The medication part.
Exactly. What the sources call the anti-seizure medication conundrum. You'd hope for clear answers, right? Like, this drug is risky, this one's safe.
Yeah, a simple list.
But it's not like that. The studies show conflicting results. For some ASMs, one paper might hint at a protective effect,
Okay.
while another points to increased risk, or maybe no effect at all, sometimes for the very same drug, or similar ones.
It's a really nuanced, kind of contradictory landscape. Makes treatment choices difficult, I imagine.
It does, and this lack of a simple answer really highlights some key clinical implications discussed in the report.
Like what?
Well, fundamentally, the need for integrated care. Cardio-neurological care.
Meaning neurologists and cardiologists really need to be talking to each other about patients.
Absolutely. Managing seizures and managing heart health, they aren't separate silos here.
Makes sense.
The sources suggest things like routine baseline ECGs and then periodic checks.
Those are the heart rhythm tests.
Yeah, exactly. Especially important if you already have other cardiac risk factors, high blood pressure, cholesterol, that sort of thing.
And this complexity must feed into choosing the right ASM for someone.
Definitely. It points towards really personalized ASM selection. Doctors need to weigh seizure control against your specific cardiac history and risks.
Are there any specific drugs mentioned as maybe being safer from a cardiac standpoint?
Well, the report does note that several studies they reviewed suggested levetiracetam and lamotrigine seem to have a more favorable cardiac safety profile compared to some others currently.
Okay, that's useful context.
But it's not just about the drugs. It's also about managing the whole picture. Holistic risk management, meaning actively looking for and treating those traditional cardiovascular risk factors, hypertension, diabetes, high cholesterol. It becomes even more critical in people with epilepsy because their baseline risk might already be elevated.
Right, because of the epilepsy itself.
Potentially, yeah.
It's clear this is still evolving. Do the sources mention where research needs to go next?
They do. There's a need to sort out those contradictions we mentioned for drugs like lacosamide and carbamazepine, for example. Finding biomarkers, maybe blood tests or scans that could predict who's at higher cardiac risk would be huge.
Yeah.
And really digging into the precise mechanisms. How exactly do epilepsy or these drugs affect things like cardiac ion channels, the tiny electrical gates in heart cells?
Well, lots more to learn then.
Definitely. So if we bring this all together for you listeners,
Yeah, the main takeaway.
it's that epilepsy and heart health are, well, deeply intertwined, much more than we maybe used to think.
Right. Understanding the risks, both from the epilepsy itself and the complex picture with medications, is just crucial.
It really is, for managing the condition effectively.
This deep dive really hammers home why we need a truly holistic approach. You have to consider heart health right alongside seizure control. It's about the whole person.
Exactly. And maybe a final thought for you to ponder.
how might this growing understanding, this idea of the epileptic heart and the complex drug effects, how might it actually change the standard of care for epilepsy down the road, pushing us towards truly integrated care where brain and heart are always considered, together?
Yeah, so there is a human in the loop. If you have any questions, go for it. Everything we do is available on this website, so go check it out as well.
All right, welcome back to the deep dive. You've handed us a really fascinating stack of source material today, and it's pulling us into, well, a connection that maybe isn't top of mind for everyone, epilepsy and heart health.
That's right.
And looking through this, it feels very critical.
Absolutely. It's a comprehensive review, essentially synthesizing findings from, a whole bunch of key studies, large data sources. It's trying to give us that bigger picture.
Right.
And the picture isn't just about simple drug side effects. It goes deeper.
So our mission here for this deep dive is to really unpack these, complex and critical links your sources lay out. We want to help you get your head around this idea that the review calls the epileptic heart.
Mm-hmm.
The idea that the condition itself poses a cardiac risk, and then try to wrestle with the sometimes surprising, pretty nuanced effects of the medications used.
Yeah, we'll guide you through the evidence for that inherent risk, dig into the, let's say, confusing landscape of the anti-seizure meds and their impact.
Confusing is a good word for it, based on my read.
It can be. And then we'll talk about what this all means for healthcare today and look at the big questions researchers are still trying to answer. It's definitely a puzzle.
Okay, let's dive in then. Start with this core idea the source puts front and center, the epileptic heart. This is where it gets really interesting, doesn't it? Because it pushes back against maybe the simpler view.
It does.
The sources are suggesting it's not just about, I took this pill, now my heart's acting up. It's that having epilepsy, according to the synthesis, seems to significantly increase the long-term risk of heart problems.
That's the really critical and maybe surprising takeaway right up front. The review pulls together data that strongly suggests this inherent link, meaning the neurological condition itself somehow predisposes people to cardiac issues over time.
And the stats cited are pretty stark.
They are. One key finding the source really highlights, it cites Lee Lane et al. From 2021, is that patients with epilepsy who are on anti-seizure meds, ASMs, they face a striking 58% higher risk of major cardiovascular events.
58%, wow, compared to controls.
Compared to controls, yeah.
Yeah.
And we're talking the big ones, heart attack, stroke.
That's huge. That's not a small number. A 58% higher risk for things like heart attack or stroke. That really reframes things.
It absolutely does. It sort of elevates epilepsy itself into a significant cardiovascular risk factor, kind of like how we think about diabetes or high blood pressure affecting heart risk.
Okay.
Yeah.
And the source backs this up with other findings, too. It points to work from Wang et al. In 2023, which looked specifically at arrhythmias, irregular heartbeats.
Right. And what did that study find, according to the review?
That epilepsy is associated with a 36% higher long-term risk of developing any kind of cardiac arrhythmia.
Okay, 36%, still significant.
But here's the bit the source really flags as noteworthy. This increased arrhythmia risk seems to be independent of genetic predisposition.
Independent of genetics. So wait, it's not just that maybe some people are genetically prone to both epilepsy and heart rhythm issues and they just happen together.
That's what this data suggests, or at least points away from. It hints that the epilepsy itself, the neurological processes involved, might be somehow directly or indirectly contributing to that arrhythmia risk. So you take these together, the 58% jump in major event risk, the 36% jump in arrhythmia risk, seemingly independent of genetics. It really establishes this concerning inherent link. It makes that epileptic heart concept feel very real.
And very critical, like you said. It connects neurology and cardiology in a way that feels, fundamental for these patients long term.
Exactly.
Okay, so we've got this baseline risk coming from the condition itself. That's quite something. But then, of course, there's the treatment. Managing epilepsy almost always means anti-seizure medications, ASMs.
Right.
And this is where the source material says things get highly nuanced and presents conflicting evidence. Sounds like the picture gets a lot murkier now.
It really does. And that murkiness is a big challenge in the clinic. The review looks at various studies on different ASMs, and, well, there's no simple pattern. Some research does link certain ASMs to maybe increased arrhythmia risk or other heart issues,
Okay.
but then other studies, sometimes really big ones, might suggest protective effects or maybe neutral effects for the exact same drugs or ones in the same family.
Wait, how can the evidence be so contradictory for the same medication? That seems tricky.
It's incredibly complex, isn't it? It probably comes down to how the drugs work differently in different people, how studies are designed, who's in the study, the doses, how long they look.
All those variables.
Yeah, and the source review doesn't magically solve these contradictions, but it absolutely highlights them as a critical challenge. It shows this complexity by looking at several common ASMs. It even has like an interactive feature in the original source material summarizing data for specific ones.
Right, I saw the list. Lacosamide, carbamazepine, lamotrigine, levetiracetam, OXC, valproic acid.
Exactly. And when you look at the summaries the source pulls together, you see this mixed bag. For drug X, maybe one big database study hints at more arrhythmias, but then a meta-analysis combining trial data might say, looks neutral. Or another database study might even suggest it's protective, maybe for certain things or certain people. The source literally uses categories like protective, increased risk, neutral for the same drug across different studies.
Sure, it's not a neat list of good heart drugs and bad heart drugs for epilepsy. It's much more, well, it depends which study you read, and we're still figuring it out.
Pretty much. And that confusing data landscape is, maybe one of the toughest parts of managing epilepsy while keeping an eye on the heart. Clinicians have to navigate all this uncertainty.
Weighing seizure control against these potential, sometimes debated, heart risks.
Exactly. Which brings us straight to the practical side. What do we do with this information?
Yes, the crucial so what question. Given this inherent risk from epilepsy, plus this complicated medication picture, what does this mean for people living with epilepsy, for their doctors? What actions should follow?
Right. And the source distills this into key takeaways for clinicians. It's that critical bridge from research to actual patient care.
Right.
First off, based on the epileptic heart risk and potential ASM impact, the source strongly recommends routine screening.
Routine heart screening for everyone with epilepsy.
That's the push. Specifically baseline and then periodic ECGs, electrocardiograms, measuring heart electricity, for all epilepsy patients.
All of them?
That's the recommendation. And it's especially strong if someone also has other traditional heart risk factors, high blood pressure, diabetes, high cholesterol, that sort of thing.
Okay.
The source really frames this as a critical step, not just a nice to have given the findings we've discussed. It's acknowledging that inherent risk.
Got it. Proactive monitoring becomes standard. What's next?
The need for personalized ASM selection. This hits that medication complexity head-on. It means doctors choosing an ASM have to consider the patient's specific heart history and risks. It can't just be about which drug works best for seizures in general.
It has to be about which drug is likely safest for this patient's heart, too.
Precisely.
Does the source offer any hints there, even with the conflicting data? Any front runners for being maybe safer?
It does offer something, and it's important to highlight this directly from the source material. It mentions that, based on several studies reviewed, levetiracetam, that's LEV, and lamotrigine LAM, currently seem to show a more favorable cardiac safety profile.
Okay, more favorable. So not a guarantee, but maybe a better starting point for some patients.
Exactly. It acknowledges the nuances, the need for more data, but it gives clinicians some guidance when they're thinking about patients with heart concerns. It's a helpful pointer amidst the complexity.
That is helpful. Okay, what else?
The third big takeaway is holistic risk management. This means going beyond just the epilepsy meds and the ECGs.
Right. Looking at the whole picture.
Yeah. Actively managing those traditional cardiovascular risk factors is crucial. Treating the high blood pressure, the diabetes, the high cholesterol, encouraging lifestyle changes.
Because those things interact with the epilepsy risk.
Precisely. They can amplify the overall cardiac vulnerability in someone who already has that underlying epileptic heart risk and might be on ASMs with uncertain cardiac effects. It's about treating the whole person, all their interconnected health challenges.
So screening, personalized meds, considering the heart, and managing overall cardiovascular health. Those feel like really critical, concrete actions.
They are actionable steps based on this compelling, if complex, evidence.
Okay, so we've covered the inherent risk, the medication maze, and the clinical actions. But science is always moving. The source also looks ahead, right? What are the big unanswered questions? Where does the research need to go next?
Absolutely. It's not a closed book. The source has a section on future research needs. And maybe the most critical one is tackling that ASM conundrum directly. The need to resolve the contradictions in the data we have now.
How do you even do that if different studies say different things?
The source points to needing head-to-head comparative safety trials, real planned clinical trials designed specifically to compare the heart effects of one ASM versus another, or versus placebo, under controlled conditions.
Instead of just looking back at database records that weren't designed for that question?
Exactly. Get rid of some of those confounding variables. The source mentions this is especially needed for drugs with the most conflicting data currently, like lacosamide and carbamazepine were examples given. It's the best way to try and settle these safety questions more definitively.
Makes sense. Gold standard research. What else is on the wish list?
A huge need is to discover biomarkers. We need reliable ways, maybe from an ECG pattern, a blood test, something non-invasive to tell us which individual patients with epilepsy are at the highest personal risk for heart problems.
So we could identify the high-risk individuals early, not just screen everyone the same way.
That's the goal. It would allow for much more targeted, personalized prevention and monitoring. Really pushing towards personalized medicine here.
That would be a game changer.
It would. And finally, the source stresses we need to investigate the mechanisms. We need to understand how these things are happening at a basic level. How do different ASMs actually affect heart cells? How does epilepsy itself maybe impact heart function electrically or chemically?
Like figuring out exactly which tiny channels in the heart cells a drug messes with?
Precisely that level of detail. Understanding those cellular mechanisms, ion channels, electrophysiology, maybe how seizure activity impacts the heart directly. That's crucial for eventually developing new anti-seizure drugs that are designed from the start to be safer for the heart.
So definitely not a settled field, lots of critical questions still open, and maybe even a bit fun for the researchers trying to solve these puzzles.
It's a fascinating area, yes. A critical intellectual challenge, absolutely.
Yeah.
There's still so much to uncover about these fundamental links.
Speaking of uncovering things, where did all the data that is in the source review actually come from? What kind of sources are driving these insights we've been talking about?
Yeah, the studies synthesized in the review, they're drawing on some really powerful resources, mostly large research databases that contain de-identified health info from like millions of people.
Okay. Any specific examples mentioned?
The source points to several key ones, like
Yeah.
the UK Biobank, that huge UK database. That's where the Wang study got its data for the arrhythmia findings.
Right.
It also mentions the Optum Labs Data Warehouse, which is a big U.S. health insurance claims database used in some cited work, and regional data, too, like the Wales UK healthcare data used by Lee Lane for that striking 58% risk finding.
So leveraging these massive pools of anonymous patient data to spot patterns.
Exactly. And besides those big databases, the source also pulls from meta-analyses. Those are studies that combine results from lots of previous trials and studies to get a higher level view, like work by Leach et al., mentioned in the source. It's about synthesizing information from many places.
Okay.
And the source also helpfully lists other valuable data sets for this kind of work, even if not used in every single cited study. Things like the U.S. Nationwide Inpatient Sample, NIS, the Canadian Longitudinal Study on Aging, CLSA, and even clinicaltrials.gov to find info on trials that might have relevant safety data.
It's good to know researchers have these tools, that they can do this kind of large-scale detective work while protecting individual privacy to find these really critical connections.
It really is. That's how these patterns, these risks like the epileptic heart or the varied ASM effects, which might have been missed before, can be properly identified and studied.
Wow. Okay, so stepping back from this deep dive into your sources, the big picture here is pretty significant, isn't it? This link between epilepsy, the treatments, and heart health, it's not some minor footnote. It's complex, yes, but critically important.
Definitely. It really underscores that for someone living with epilepsy, their heart health is deeply connected to their neurological condition. That epileptic heart concept highlights an inherent risk.
Right.
And then the ASM data adds all these layers of complexity that just demand careful thought.
And the clinical implications we discussed feel very clear, very critical. Routine heart screening, personalized medication choices, thinking about the heart, and really managing those other cardiovascular risks aggressively.
It's definitely a challenge for clinicians and patients, navigating seizure control alongside cardiac safety. But hopefully the insights from this kind of review offer a clearer path forward for better care and show exactly where we need more research. Given those persistent contradictions and how different ASMs seem to affect the heart and this urgent need for biomarkers, how might future research truly unlock the ability to predict and prevent specific cardiac risks for each individual patient, moving beyond just population averages to truly personalized cardiac care in epilepsy? That's maybe the most exciting and critical challenge ahead.
Something definitely to think about as this field keeps evolving. Thank you for bringing this, vital and really fascinating topic to us today. That's all for this deep dive.
Yeah, I'm not sure how relevant the data sources are. They probably are not very relevant. Okay, let's see. Yeah, so the data set don't seem to be. Wait, so those are other data sets. Here we have NIS. Do the links work? Should not hallucinate links anymore. This seems to be working okay. Yeah, it will be quite hard finding any specific data in it. Apply for data access. But yeah, we're not doing that. If the data is not available publicly, we are not using it. And this is search on clinicaltrials.gov. So it would be actually interesting reviewing some clinical trials. And let's actually do a quick. Okay, if we have epilepsy. So actually, yeah, EEG in epilepsy is actually not a treatment, it's just monitoring. So put it in EEG intervention treatment. Yeah, we'll leave that. All studies. Let's search how many studies are there. There are 570 studies from Italy, from US, United Kingdom, Belgium. Yeah, that's interesting. So you have 2 suspended, 23 withdrawn. Okay, those would be quite interesting because the question is why were they withdrawn? Recruiting 136. How come there's like 570 all up? Ultra long term EEG monitoring is actually quite interesting. It's recruiting. It's a new study. Might look into that. Okay, no results. They're just recruiting now. Yeah, the publications are not from the study. They might be general. Hey, open label, 12 years plus. Are they mentioning devices? Wearable at home, EEG device. What's the difference between study details and researcher view, assuming researcher view has more details in it? So drug-resistant seizures, there's an age inclusion criteria. Yeah, it's kind of standard exclusion criteria. Interesting enough, a subject with a cochlear implant will be excluded from a study. Well, how about a cochlear implant that was actually a similar implant? How about an implant that actually used to record epileptic seizures? Would those patients be excluded? The short answer is yes, definitely. Quite an interesting one. Let's pop it into Notebook LM. Enrolling by invitation.
Okay, let's just dive straight in. There's this fundamental challenge for people with epilepsy and for their doctors, too. It sounds simple, but it's actually incredibly hard. Knowing exactly how often seizures are happening.
It really is. You'd think just count them, right?
Exactly. But relying on memory, or maybe a diary someone keeps, our source material makes it clear pretty quickly that, well, that approach has some major limitations.
It absolutely does.
Yeah.
Subjective reporting, like those diaries, they're often unreliable. And it's not necessarily anyone's fault. It's inherently difficult.
How so?
Well, think about it. Some seizures are subtle. Maybe the person doesn't even realize it happened fully, or they happen during sleep, or the seizure itself affects memory right afterwards. How can you reliably record every single event?
That makes sense. And the source material, it specifically points out this is a big issue for certain groups, right? Like people with intellectual disabilities, where reporting might be even tougher.
Precisely. And this isn't just, an academic problem. It matters hugely for treatment.
Right, because if you don't know the real frequency, how do you manage things? Like medications, adjusting doses.
Exactly. Or evaluating if a treatment is even working properly, or deciding if someone needs more support, like supervision at night, perhaps. All these crucial clinical decisions hinge on having an accurate count. An unreliable number means you're potentially flying blind.
So this obvious gap.
Yeah.
How do we fix it? And this is where our deep dive into the source material gets really, really interesting today. We're looking at a clinical trial that's tackling this exact problem using technology.
It's called the eARLU study. That stands for Home Ultra Long-Term EEG Monitoring for Rare Epilepsies and Developmental and Epileptic Encephalopathies. Quite a mouthful.
Yeah, but the key part is home ultra long-term EEG monitoring. You can find the details on clinicaltrials.gov. The ID is NCT 0685901 if you want to look it up yourself.
And the core idea, the mission of this study, It's pretty straightforward, but potentially revolutionary. Use a wearable EEG device, one that's minimally invasive, to monitor brain activity continuously for a very long time while people are just living their normal lives at home.
Okay, wearable EEGs sounds familiar, but this study uses something specific, right? Ski-EG.
That's right, subcutaneous EEG. So the electrodes, the sensors, they're actually implanted just beneath the skin.
Wow, okay. Subcutaneous. That does sound a bit sci-fi.
A little, maybe. But the aim is to get really robust, continuous data over weeks or even months, not just the hours or maybe days you might get in a hospital setting.
So you get a picture of seizures in the real world, not just the clinic.
Exactly. The goal is a more precise, patient-centered way to manage epilepsy based on what's actually happening day to day.
And the study itself, how's it structured? The source calls it an open-label, non-pharmacological interventional prospective study. Let's unpack that a bit.
Okay, so open label means both the researchers and participants know what the intervention is. There's no placebo device here.
Yeah.
Non-pharmacological means they're testing the device, the monitoring method, not a new drug.
Got it. And interventional perspective just means they're actively introducing the device and following people forward in time to see what happens. With a single group, everyone gets the ski-EG.
Correct. It's all about evaluating this monitoring approach itself.
So who's actually in this study? Who are they recruiting?
The criteria are pretty specific according to the source. Participants need to be 12 years or older. They generally have drug-resistant seizures, meaning meds haven't fully controlled them, or specific conditions like rare epilepsies or these developmental and epileptic encephalopathies, DEE. And crucially, they need to have already been well evaluated, usually in specialized clinics or epilepsy monitoring units, so their seizure types are already known and characterized. This isn't for initial diagnosis, it's for better management of known, difficult-to-treat epilepsy.
So focusing on people where getting that accurate count is probably most needed.
That seems to be the idea.
What about who isn't eligible? Sometimes the exclusion criteria are just as revealing.
They are. The source lists quite a few. No major uncontrolled psychiatric disorders, for instance.
Yeah.
No active infections or skin problems right where the implant would go. Obviously, people at high risk for surgery complications are out.
Makes sense. Anything surprising?
Well, maybe a couple of things. People with certain other implanted electrical devices nearby, like cochlear implants, are excluded. Presumably, that's an interference concern.
Oh, okay.
And this one's interesting activities with a high risk of trauma to the device area, like martial arts, are mentioned specifically.
Okay, so no sparring with your subcutaneous EEG.
Apparently not.
Yeah,
Also, you need to be able to actually operate the recording device or have a caregiver who can help manage it. And pregnancy is an exclusion, too.
Right, so it really highlights who this is designed for. People with specific, challenging epilepsy types, where the benefit of objective data outweighs the procedural aspects, and where it's safe and practical to implement.
Exactly. And the study itself unfolds in two main parts. Part one is all about calibration, and it happens in the hospital.
Okay, tell us about that.
So first, the ski-EG electrodes are implanted. It's described as minimally invasive. Then, the participant is admitted to an epilepsy monitoring unit, an EMU.
That's the standard hospital setup with continuous video and scalp EEG monitoring.
Precisely. They stay there for anywhere from 2 days up to about 2 weeks.
And the purpose of this hospital, stay with the new ski-EG already implanted.
Validation. This is critical. They're recording data from the new ski-EG device at the same time as they're recording with the gold standard video EEG.
So a direct comparison.
Exactly. They want to see how well the ski-E performs. Does it detect the seizures confirmed by the video EEG? What's its sensitivity? Does it generate false positives, false negatives? They're really testing its accuracy against the best current method.
And safety too, presumably. Short-term safety.
Yes, short-term safety is monitored closely during this phase. And they also start testing the automated seizure detection algorithm with this initial high-quality verified data set.
Okay. And you mentioned something about blinding earlier.
Yes, very important. The clinical experts who review the ski-EG data during this validation phase, they are blinded. They don't get to see the video EEG results simultaneously.
So they're judging the ski-EG purely on its own signals, no peeking at the answer key.
Exactly. It ensures the performance assessment is objective.
Right, that rigor is key. Okay, so once the ski-EG is calibrated and validated in the hospital, then comes part two.
Then comes part two, the home monitoring phase. This is the real core of the study. testing the device out in the wild, so to speak.
Out in the wild, living everyday life. For how long?
Participants go home with the device implanted and operational for at least 12 weeks. And there's an option to extend that monitoring period up to 24 weeks.
24 weeks? That's potentially half a year of continuous brain activity monitoring at home. That's quite something.
It's a huge amount of data potential.
Yeah.
Far beyond what's typically possible.
So during those months at home, what exactly are they tracking?
Several things in parallel. First, obviously, the EEG data itself is being continuously recorded. The device also tracks when it's being used, login usage times.
Okay, the raw brainwaves.
Second, the participant, or their caregiver, keeps a seizure diary, just like before, noting down any events they perceive, time, date, what happened.
So they keep the subjective diary going.
Yes, and that's crucial for the comparison later. The source notes that these diary entries are then carefully reviewed and classified by an experienced epileptologist. They try to determine if the described event was likely epileptic or not, and what type it might have been based on the description.
Got it. Objective EEG, subjective diary. Anything else?
Yes, the third stream is safety data. They systematically collect information on any adverse device effects, or ADEs, any unintended potentially harmful effect related to the device itself or the implantation procedure.
Okay, so we've got this flood of data coming in. Continuous EEG, the person's own log, and safety checks. How on earth do they process all of that, especially the EEG data?
Yeah, crunching that much long-term EEG data is definitely a challenge. The force describes a multi-layered approach. First, there's a visual review.
By humans.
Yes, trained neurophysiology technicians review the raw EEG data, usually on a weekly basis. They're scanning for patterns that look like seizures.
Okay.
Their findings, any potential seizures they flag, are then validated by an expert clinical neurophysiologist, like an epileptologist. But here's the key again. During this visual review, both the technicians and the experts are blinded.
Blinded to what this time?
They're blinded to the patient's seizure diary. They don't know what the patient reported happening when they're looking at the waveforms.
Okay. So the human EEG readers are judging purely based on the electrical signals. What about the automated side? You mentioned an algorithm.
Right. In parallel to the human review, there's an automated detection algorithm running. It analyzes the same EEG data completely independently, looking for seizure signatures based on its programming.
So the computer takes its own pass at the beta.
Exactly. And then the results from that algorithm are also reviewed by investigators. But these investigators are blinded to the results of the human visual analysis.
Wow. Okay, so multiple layers of blinding. You've got the diary, you've got the human EEG readers blinded to the diary, and you've got the algorithm results reviewed by people blinded to what the human readers found.
Precisely. And this is where it gets, as you said earlier, really fun in a data nerd kind of way.
Yeah.
You end up with 3 different measures of seizure frequency for the same period. What the patient reported, what the human experts found by looking at the EEG, and what the algorithm found in the EEG.
And comparing those 3, that must be incredibly insightful.
That's the goal, to objectively see where the discrepancies lie. How much does the diary underreport or misinterpret events? How well does the algorithm perform compared to expert visual review? It lets you quantify the value and limitations of each approach.
That comparison feels like the real payoff here. It's not just, can we record EEG at home? It's, what does that recording tell us compared to what we thought we knew?
Exactly. And alongside all this data crunching, they are, of course, rigorously tracking the safety and tolerability aspect we mentioned.
Right, the ADEs, even though it's minimally invasive, procedures aren't risk-free.
Absolutely not. Safety is paramount. They collect reports of any issues from the participants or their diaries. These ADEs are then classified carefully mild, moderate, or severe, and they determine if any are serious, meaning they require hospitalization, are life-threatening, or cause significant disability.
Does the source list the kinds of things they're looking out for?
It does. It gives a specific list of potential ADEs, things like hematoma, which is like a deep bruise, or collection of blood, or seroma, which is fluid buildup under the skin, pain or headache, obviously, risk of infection at the implant site, general discomfort. There's also mention of potential skin issues if the device causes pressure, like ischemia or reduced blood flow, or even necrosis, which is tissue damage, plus swelling, soreness, irritation, or itching around the device.
Okay, so they're being very thorough in tracking the downsides, too. It grounds the cool tech in the reality of the patient experience.
It has to. For any new approach to be adopted, the benefits need to clearly outweigh risks and burdens.
So let's zoom out then. Assuming this works well and the safety profile is acceptable, what's the potential impact? What does gathering all this objective, long-term, real-world data actually mean for people with epilepsy? So what does this all mean?
Well, connecting those dots, the potential is pretty significant. First and foremost, it gives you that objective measure of seizure frequency. You can finally compare the diary count to the SCIEG count and see the reality.
Quantify that suspected underreporting.
Exactly. Get a real number on it. And knowing that actual frequency, that directly impacts treatment decisions.
Right, like adjusting medications.
Precisely.
Mm.
You can make changes to anti-seizure meds and then objectively see if they're working better, worse, or the same based on the SCIEG data, not just hoping the diary changes. It can take a lot of the guesswork out of finding the right treatment plan.
That makes sense. And you mentioned earlier about patterns, circadian rhythms and things. That sounded really interesting.
Yes, that's another potentially powerful outcome. Analyzing months of continuous data lets you see if seizures tend to cluster at certain times of day that's circadian, or maybe follow other cycles, ultradian patterns occurring more than once a day.
And knowing when seizures are more likely.
Allows for truly personalized safety plans. Imagine knowing someone is at significantly higher risk between, say, 2 a.m. and 4 a.m. That could inform specific precautions, caregiver awareness, maybe even timing of certain medications. It's about proactive management based on the individual's objective patterns.
That feels much more targeted than just general precautions. And what about the need for support? If the device reveals way more seizures than anyone realized.
That's another key point. If the SCIEG shows a much higher frequency, especially seizures the person wasn't aware of, like nocturnal ones, it provides objective evidence that maybe more support is needed.
Like supervision or changes to make the living environment safer.
Exactly, especially for people living alone or those with cognitive challenges. It helps make the case for necessary support based on data, not just estimation. The ultimate aim, as the source material really emphasizes, is to improve quality of life.
How so?
By enabling more effective disease management to happen primarily at home, minimizing hospital stays, and tailoring treatments much more precisely based on what's actually happening in the person's brain during their everyday life. It's about using objective, real-world data for better, more personalized care.
Okay, so wrapping up this deep dive then. We started with this fundamental problem. Just how do you accurately count seizures? It's harder than it sounds.
Much harder.
And this E-Meyer study we looked at offers a potential solution using this minimally invasive SCIEG technology for ultra long-term monitoring right in the person's home.
It's a fascinating attempt to move beyond those often unreliable subjective diaries and get objective data that can be surprisingly precise and really valuable for management.
It's really about getting a clearer, quantified picture of the true burden of epilepsy, revealing frequency and patterns we just couldn't see reliably before.
Augmenting, maybe even eventually shifting, how we assess seizure severity and treatment response.
And that brings us to a final thought for you, our listener, to maybe chew on. If this kind of technology proves successful getting detailed, objective, continuous brain data from someone living their normal life for months, where else could this go?
Yeah, it makes you wonder, doesn't it?
What other neurological conditions, what other questions about brain function or dysfunction could benefit from similar long-term real-world monitoring? Think about things like, I don't know, migraine patterns, maybe sleep disorders like apnea, or even tracking subtle changes in movement disorders. What could we learn if we could watch brain activity unobtrusively for extended periods?
It definitely opens up some intriguing possibilities for the future of neurology and patient care.
Something to think about. Thanks for joining us for this deep dive into the EMIO trial and the quest for objective seizure monitoring. We hope it gave you some interesting things to consider.
Yeah, there is a human in the loop if you have any questions. Sorry, I have a bit of a cough, so... Well, we're normally using a lot of AI robots, but especially today when I'm about to lose my voice or when I'm talking too much, I actually start coughing. And luckily I have the microphone very close to the hole in my face. Yeah, the DJ. Keep losing the DJ. Keep losing the DJ. We keep losing the DJ. Can we actually save those? No. About... Can we actually turn this into a prompt? Real quick, we use 2.5 flash, so it's faster. What you see on the screen for the music, we have an AI music generator. Can you turn this into a standalone detailed prompt? Text prompt? Let's give it to Gemini real quick. Because we want to be able to recreate. I'm not sure. What? That's... can you actually stick to the image I provided and rewrite the prompt? It's going places. Well, that's only because I was fairly vague in my request. So let's try it again. Let's try it again. Yeah, that's interesting. Now just go for that one. Let's close this. That page is just Gonski, Google Apps. We're using music effects. Generate musical track using the following: soprano saxophone, bass clarinet. Yep. Score the overall field should be tight groove. Okay. That's interesting. And we should not have any copyright issues with it, should we? No. Well, because something went wrong. Try the prompt again. Okay, let's try again. Why is it a complicated prompt? So we actually got this prompt from the DJ. Maybe it didn't like that first part of the sentence. Because with music effects, you probably don't need to. Should we split it into two parts? I don't get it. Okay, let's go back to the DJ. Don't think it's following instructions. That's a bit unfortunate. Okay, now we're talking. Okay, now we're going places. And the memory for this tab is already 342 megabytes. That's quite a bit. It's really good, actually. Love it.
Welcome back to the Deep Dive. Today, we're diving into, well, it looks a bit like a government report at first glance, but inside this stack of source material, there's some really fascinating stuff about epilepsy research.
That's right. We pulled excerpts and search results straight from clinicaltrials.gov. And we got pretty specific.
Yeah.
Focused on epilepsy, studies involving EEG, measuring brain waves, and also some kind of implant intervention. It's a very particular slice.
Okay, so our mission today is basically to guide you through this potentially dense list.
Exactly.
We want to unpack what this snapshot actually tells us about what researchers are doing, like right now, globally, in this area.
Cut through the jargon, find the interesting bits.
Yeah, find the nuggets. It's like peering into one specific corner of the huge effort to tackle epilepsy.
And the source itself, clinicaltrials.gov, it's the official U.S. database, run by the National Library of Medicine. Many studies from around the world have to register there. It's supposed to be a central place to see what research is happening, planned, finished, all the details.
Purpose, participants, locations, that kind of stuff.
And our search, like we said, epilepsy, EEG, implant. We also saw a note that the site's getting a big update in June 2025, which is good for the future.
For sure.
But we're looking at the data listed right now.
Okay, so what does that data look like? First off, the numbers.
Well, the first thing is just the volume. For that very specific search, 44 studies listed.
44. Wow, okay.
Yeah, it tells you this isn't some tiny, obscure corner. It's an active field.
So 44 studies. The database breaks them down by status, right? What does that tell us?
It does. It gives you a sense of the research life cycle. So 16 are listed as recruiting.
16. That means they're actively looking for people right now.
Exactly. Moving forward, needing participants to, test their ideas or devices.
Okay. Then 11 are completed. That's good news.
That's the goal, yeah. Finish the study. And even better, 4 of those 11 actually have results posted.
Ah, crucial. Getting the findings out there.
Definitely. Then you've got 3 active, not recruiting, probably finished enrollment, still monitoring or analyzing data.
Makes sense.
3 not yet recruiting, so they're listed, maybe approved, but haven't started taking people yet. And 3 enrolling by invitation.
Which suggests maybe very specific patient groups.
Could be, or specific recruitment methods. Then, research doesn't always go smoothly.
Right.
3 studies are listed as withdrawn, and 1 was terminated.
Oh. But you mentioned something interesting about that terminated one.
Yeah, it did post some results. So even if a study stops early, sometimes there's still valuable data to share, which you could practice.
Definitely. Okay, what else?
And then there's, a little touch of real-world messiness. 4 studies have unknown status.
Unknown.
Yeah, with an asterisk. It means they're past their estimated completion date, but nobody's updated the status in over 2 years.
Huh. So things can just kind of drift off in the database sometimes.
It shows the challenge of tracking all this complex global research, right? It's not always perfectly up to date.
Yeah, it's a reflection of reality, not some perfectly clean data set. Okay, so beyond status, who are these studies for? Age groups.
Good question. All 44 include adults, 18 to 64. Most, 39, also include older adults, 65 plus. And 10 studies include children.
Children, so from birth to 17.
Right, so it really does span the whole lifespan, which is important for epilepsy.
It is. Now, here's something that seemed a bit surprising in the notes. Healthy volunteers.
Yeah, 5 of these studies accept healthy volunteers.
For studies involving brain implants and epilepsy, why would they need healthy people? Seems counterintuitive.
It does raise an eyebrow, doesn't it? But it's likely for a few reasons, maybe establishing baseline brain activity with that specific device.
Okay, like a control group for the tech itself?
Sort of. Or calibrating equipment in a non-epileptic brain, or maybe comparing brain patterns directly between healthy folks and those with epilepsy.
Ah, okay. To better understand the disease or test how sensitive the device is.
Exactly. It shows that this implant research isn't just about the treatment, it's also about refining the tech and understanding the basic science.
Got it. What about the type of study? Mostly intervention, I assume?
Overwhelmingly. 41 out of 44 are interventional. Only 3 are observational.
Which makes sense, given our implant filter. Interventional means they're doing something, like putting in the implant or using it to stimulate.
Right. Whereas observational might just mean they're using an existing implant to record data without testing a new treatment with it. So yeah, implants usually mean intervention.
And the study phase? I saw mostly not applicable. That seemed odd. 40 out of 44.
Yeah, that looks weird if you're thinking about drug trials with phase 1, 2, 3.
Right.
But for devices, especially surgical implants, those phases often just don't fit neatly. A lot of these might be, first in human tests or safety studies or just checking if the device works as intended.
So not applicable is actually pretty common for this kind of device research.
Very common, yeah. It doesn't map well to the drug development pathway.
Okay, enough stats. Let's get into the really interesting stuff. What are these studies actually looking at? Any major trends popping out from the titles or summaries?
Definitely. One big one is subcutaneous EEG. That phrase or related concepts popped up quite a bit.
Subcutaneous, under the skin, right. Not quite on the scalp, not quite in the brain.
Exactly. We saw studies mentioning it specifically, like ones in the UK, Denmark, and a multi-site one, including the US.
So what's the advantage there? Why go under the skin?
It's aiming for a sweet spot. Regular scalp EEG is non-invasive, but it can be messy, prone to errors from movement, and hard to do continuously outside a hospital. Intracranial EEG inside the skull is super precise, but, well, it requires brain surgery, major surgery.
Yeah.
Subcutaneous aims for the middle, implanted just under the scalp skin, hopefully giving more stable, reliable signals for potentially months or even years.
For long-term monitoring in a person's normal life?
That seems to be the goal. Could be huge for tracking seizures or treatment effects outside the clinic. 257 monitoring potential.
That leads right into another trend we spotted. Ultra-long-term EEG monitoring.
Yep. Studies explicitly focused on this, some running in Italy, Denmark, Ireland. That multi-site one again.
Ultra-long-term. How long are we talking?
Potentially months or years, enabled by these subcutaneous or other types of long-lasting implantable devices. The idea is to capture infrequent seizures or other brain events that you just miss with short-term EEG.
Right, because some people only have seizures rarely or triggers are subtle.
Exactly. Or understanding sleep patterns, how therapies are working over the long haul, things you just can't see in a snapshot. And the locations listed really drive home that this is a global push.
Okay, so that's the less invasive long-term angle. What about the other end, the really invasive stuff, electrodes inside the head?
Oh yeah, that's heavily represented too. Lots of studies mentioning intracranial EEG, and then all sorts of specific electrode types.
Like what?
Well, you see terms like hybrid micro-macro electrodes, Microelectrode arrays, just microelectrodes. Subdural electrodes.
Subdural sits on the surface of the brain under the skull bone.
Right. And then a lot of SEEG, stereoelectroencephalography.
Which involves inserting thin probes deeper into the brain structures.
Precisely. These studies, often identified by their NCT numbers, those unique codes on the website are usually part of evaluating patients for possible epilepsy surgery.
Ah, to pinpoint exactly where seizures are starting.
Exactly. You need incredibly precise mapping for that. Subdural grids cover the surface, siege probes go deep. Depends on where they suspect the seizures originate. These microarrays and things get even more granular. It's highly technical.
So really invasive, but necessary for surgical planning in some cases.
Critical information, yeah.
So you've got this contrast. The push for less invasive, long-term monitoring for maybe broader management, and the continued use of highly invasive, super precise mapping for specific treatments like surgery shows the field is working on multiple fronts.
Absolutely. And what's really fascinating is that it's not just about finding seizures.
Oh.
We saw studies explicitly linking epilepsy to other things, like mood. There were a couple in the US looking at epilepsy and depression specifically.
That's really important. The mental health impact of epilepsy is huge. Are these studies just correlating seizure data with mood diaries, or?
That's a great question. The summaries would have the detail.
Right.
But the fact that they're using these implants tools designed for EEG to investigate mood shows a broader perspective.
Thinking beyond just the seizure itself.
Right. And we also saw studies looking at memory and general cognitive function too. It acknowledges epilepsy isn't just about seizures. It's a complex condition affecting lots of brain networks.
Using these powerful recording tools to understand the wider impact. Okay. Now, we found one study that seemed a bit different.
Ah, yes. There was one, NCT 04673071 in Vietnam, listed with that unknown status like those other mystery ones.
And the intervention wasn't a high-tech implant, it was
Thread embedding acupuncture.
acupuncture. In a list with brain implants and microelectrodes.
Right. Presumably, the embedded threads are considered the implant for the database's purposes.
Okay.
It's kind of a perfect, slightly critical example of the database's nature. It lists what's registered, but remember the disclaimer?
Yeah, the U.S. government lists them, but doesn't necessarily review or approve the science or safety of everything listed.
Exactly. It's a registry, not necessarily an endorsement.
Yeah.
So you get this incredible diversity, from cutting-edge neurotech to, well, thread embedding acupuncture. Adds a bit of unexpected flavor to the data.
A quirky data point. And speaking of diversity, the locations, we mentioned a few, but it's really global, isn't it?
Totally. Beyond the US, UK, Denmark, we saw Italy, France, Switzerland, China, Australia, Czechia, Vietnam, Germany, Belgium, Ireland, probably others too.
It's a worldwide effort.
Truly. And funded by a mix too. NIH, National Institutes of Health in the U.S. industry, which are probably device makers, and then a big catch-all category. All others like universities, other organizations, individuals. It takes a village, basically.
So we've waded through all this technical detail. Why should you, the listener, care about this snapshot from clinicaltrials.gov?
Because it's a peek behind the curtain. It shows you where the actual research effort and money are going right now in this specific area of epilepsy tech. It's not just headlines, it's the real studies being done.
Yeah, it moves beyond vague ideas about future tech and shows what's being tested in people today. You get a real sense of the scale, the global nature of it.
And the types of approaches. That contrast between less invasive long-term monitoring and the super precise invasive stuff.
Plus, seeing that the research is expanding to look at mood, memory, cognition, it shows how complex the problem is and how the tools are being used more broadly.
It really highlights how multidisciplinary it is, neurology, engineering, data science, psychology, all coming together. It's a tangible look at the cutting edge, straight from the source data.
Exactly. We took this specific slice, epilepsy EEG implants, on clinicaltrials.gov and found this really dynamic picture. Less invasive monitoring, precise surgical mapping, links to cognition and mood happening all over the world.
It paints a picture of really intense, varied research activity, driven by tech advances and just a deeper need to understand the brain.
All pulled directly from that source material we looked at, which leads us to a final thought for you. When you see the kind of sophisticated brain interfaces being tested in these studies, devices that record, maybe even stimulate specific brain circuits, How dramatically do you think the way we monitor and treat conditions like epilepsy might change? Not in some distant future, but maybe in your lifetime.
Yeah, and what questions does that raise? As we get better at putting tech in the brain for diagnosis, for therapy,
Yeah.
what about, data privacy from our own thoughts?
Yeah.
Or individual autonomy? How does it change our sense of self when tech gets that integrated?
Definitely something to think about.
index.html. Add audio review files, MP3 and WAV, to the overview section and a link to the PDF report at the bottom of the page. Existing code.
Welcome. We're doing
Things like ECGs, those tests that measure, looks neutral. Or another database study
Here's how to remove the unnecessary styling from the code. Remove the render
like lacosamide and carbamazepine.
And the results are all over the place. It's really inconsistent.
It is. There's the nuances, the need for more data, but it gives clinicians some guidance when they're thinking about patients with heart concerns.
Continue to iterate? Copilot has been working on this problem for a while.
I'm not sure why it takes the GPT 4.0 in agent mode. It was just reading the code base for quite some time. Now it's meant to be editing. All I asked is to remove comments from the view. That's not good. And let's go back to editing mode. I don't know if a Gemini 2.0 Flash should do it. Hey, can you keep the rest of the code as is? So we just remove
Okay,
comments.
I will remove the comments from the code while keeping the rest of the code as is.
Okay, you can do it quietly. You can do it quietly. And yes, everything we do on this channel is available on BioniChaos.com. Go check it out and provide your feedback. Fairly easy. Okay, Gemini couldn't do it as well. That's a bit odd. Okay, someone, a 2.5 Pro, Gemini 2.5 Pro should have a huge context window and stuff. Apparently we're hitting some limit. I mean, we have it standalone as well. But we are ready for production, so we won't be pushing the code. Oh, we will be pushing it into production, not back to the developer. Not back to the developer. Okay, it's actually applying changes. 80% feels quite promising. We normally do not go over the code, well, because we are vibe coding. It's meant to just remove comments. Seem to have done it pretty well. Thank you very much. can make it ready for production, so we can play with this tool. We only need to add a few things. And this header. Might have to clean up the styling some more. Okay, we should be ready for production, kind of. Yeah, there is a human in the loop, by the way. If you have any questions, go for it. Otherwise, we'll just end up talking to robots. Which, yeah, not sure which one's better or worse. Really not sure. In theory, humans meant to be better. But that's only in theory. Reality is very, very different. It will all end up working for robots. That's for sure. That's for sure. Yeah, we have some pages that are a bit problematic, to say the least. And we have a new tool as well. We have a bunch of new tools, actually. That should be pretty exciting. Yeah, we had a few videos on those as well, so yeah, we need to update a few things about them. This one has audio as well, which might be a bit annoying. It's funny. It's funny that when I talk, I actually lose viewers. That's interesting. It's very interesting. We had the demo mode for this one as well. It's actually buried somewhere. Demo modes are nice because if the user is not clicking anything, it can just do its own thing, like a simulation routine, as if the end user is actually pressing buttons, even if they're not. So it can be handy. That can be handy. Yeah, the title is pretty generic as well, which is unfortunate. Okay, we have a demo there. sure what this sound meant to do. So if you're having a focal seizure, start simulation. Yeah, that's pretty annoying. The sound is super annoying. Well, that's why it's disabled by default. That's why it's disabled by default. Disable. Where's the... Okay, we already have it deployed, but it's not quite ready. Well, we can deploy, we just don't share the link, so it's like unlisted. It's only if you're watching the live streams, you would know about it. So there's only one HTML file, which is interesting. We have the code, we have an updated version of the code. A346. Oh, 409. Okay, that should be fine. Let's see if it's working locally. Yes, it is. Play demo should go through stuff. Should be able to turn the demo off. It keeps going. Can't turn it off. It's a bit of a problem. Yeah, we're having the usual warnings. Should not be a big problem. I mean, you can restart the page. Hey, can you quickly explain how the demo mode works? So when I also specifically when I press the play demo button, it goes through the demo. Am I able to stop the demo or not? Just explain.
Okay, I can explain that. I'll add comments to the code to clarify how the demo mode operates and address the ability to stop it. Index.html. Add comments to the play demo function explaining its operation and the current lack of a UI feature to stop an ongoing demo. //
Okay, we don't need to read the code. Yeah, and we were in editing mode. Okay, can you actually change the code if necessary, and explain in the chat how did you address the play demo continuous issue? Are we now able to stop the demo mode or not? Okay, this might be loud. It won't actually work.
I've modified the code to allow you to stop the demo mode. Here's how it's addressed. Stop demo button. When you click play demo, the button's text changes to stop demo. Stopping mechanism. Asterisk a flag demo stop requested is set to true when you click stop demo.
Okay, we can do that quietly. Okay, that was quite something. That was quite something. Okay. Well, yeah, the sounds are disabled by default, so that should be better. Should protect your hearing. Okay, now it will cycle through the things. You can stop demo, stopping demo. Okay, but why does it take so long? Or will it just go through the current? Through the focal seizure and then stop, or what's up? Play demo. Why is it stopping the demo forever? Just better to restart the page or something. We will be deploying this for better or worse.
Okay, I've removed the comments from the JavaScript code. Regarding the delay in stopping the demo. The previous logic for the demo mode involved start simulation initiating its own set of time stages, before, during, after, reset, over 20 seconds. The main play demo loop then had an additional 20-second await period after calling start simulation before it would start the next seizure type or check if a stop was requested. This meant that if you clicked stop demo, the loop might still be in that additional 20-second waiting period, or the current start simulation would continue its full 20-second cycle if not interrupted effectively. I've refactored the logic. Start simulation now returns a promise. This promise resolves when the simulation's full 20-second cycle completes naturally, or if demo stop requested becomes true, in which case it resolves earlier. The play demo function now awaits this promise from start simulation. This means it waits for the current simulation to actually finish or be properly interrupted before proceeding or stopping. When you click Stop Demo, * the demo stop requested flag is set. * any active timeouts for the current simulation stages are cleared. * the start simulation function, which is being awaited by PlayDemo, sees the demo stop requested flag and resolves its promise early. * the play demo loop then breaks, and a final reset simulation cleans everything up. * visuals and I've reviewed your code. Here's an explanation of a major potential issue and a minor observation. Index.html. The script has a potential major issue related to stopping the demo mode and a minor issue regarding unreachable code. Major issue: demo mode stop mechanism can cause a hang. Explanation. When the stop demo button is clicked, the event listener sets demo stop requested equals true and, crucially, calls clear all simulation timeouts. The play demo function iterates through seizure types, calling await start simulation type for each. The start simulation function returns a promise that resolves after its internal timeouts complete, e.g., after simulation_duration. If clear all simulation timeouts is called by the stop demo button's event listener, it clears the timeouts that the currently running start simulation instance relies on to eventually resolve its promise. As a result, the promise that PlayDemo is awaiting might never resolve. This would cause the PlayDemo function to hang, preventing it from completing its cleanup, like calling reset simulation and resetting demo stop requested to false, and the UI might remain stuck in a stopping demo state. The start simulation function has internal checks for demo stop requested within its timeout callbacks. These checks are intended to allow a graceful exit and resolve the promise. However, if the timeouts themselves are cleared externally before these checks can run, this graceful exit path is removed. Minor issue: unreachable code and simulation_duration timeout. Explanation. Inside the start simulation function, the final set timeout callback, the one set for simulation_duration, has a series of conditional if/else if blocks. The final else block, JavaScript, //
Exactly. We can also do this with sound, but the sound might be annoying. So this meant to be the baseline sound of the brain. You sonify the brain, of course, activity. Can we actually check something in the code during a atonic drop seizure? Can we check something quickly in the code? During atonic drop seizure, the brain doesn't come back, so it supposedly drops on the screen, but then it never recovers. Like for when we play the demo for the next seizure type, is it supposed to be coming back? Can you check the code and explain? Can you explain in the chat? Please explain.
Okay, I've reviewed the code, specifically how the atonic seizure affects particle positions and how the simulation handles transitions between seizure types in demo mode. Here's an explanation of whether the particles are supposed to return to their original positions. Yes, the brain particles are definitively supposed to return to their original positions after an atonic seizure finishes and before the next seizure type begins in the demo. Here's why, based on the code. Atonic seizure effect, update seizure effect function. Asterisk during an atonic seizure, the update seizure effect function directly modifies the y coordinates of the particles to simulate the drop. It calculates the new y position based on the initial positions and an intensity factor. Positions.setY, I, initial positions, I asterisk 3 plus 1, 1 intensity, asterisk 20. Asterisk this means the live particle data is altered to show the drop. Resetting particle positions, reset particle state function. Asterisk there's a dedicated function reset particle state whose job is to return the particles to their default appearance and original positions. Asterisk for positions, it does this by reassigning the geometry's position attribute using the initial positions array, which was stored when the simulation first initialized and is not modified by the seizure effects. BrainParticles.geometry.set attribute, position, new 3.buffer attribute, initial positions, 3. BrainParticles.geometry.attributes.position.needs update equals true. How demo mode handles
So we don't need to update the code for this one. It meant to work already, is it?
Yes, that's correct. Based on the code review, the simulation is designed to reset the particle positions after an autonic seizure and before the next seizure type in the demo. No code changes are being proposed because the logic for this reset is already in place.
Okay, but that's not working quite as expected. So after the brain drops, or after the head falls, it's not coming back, regardless of what I do. Can you check the code again?
You are right to point this out. My apologies. On closer inspection, there's a subtle issue in how the initial positions array and the geometry's position buffer are handled, specifically for the autonic seizure. Here's the problem. In init, initial positions, a float 32 array, is created. Then, brainparticles.geometry.set attribute, position, new 3.buffer attribute, initial positions, 3.
Okay, we can do that quietly. Supposedly it found the problem. Just suggesting 2 minor changes. And we are vibe coding, so we are not reading the code. If you want to read the code, you can do it. You can do it yourself. Okay, so we have this, the brain dropping when we it's fine. No, it's not funny. Like, there's nothing funny about an atonic seizure. I'm just trying to check the code. I'm saying the code, the simulation is a bit weird. Cannot seem to actually work. Is the sound still there? Not sure. Yeah, we could use an explanation. The sound stopped working. It's a bit odd. Let's reset for a sec. Focal seizure stat simulation. Okay, it's working again. To restart the page or something. So it's for focal seizure simulation. We have to kind of wait for it to finish. Okay, when the simulation is playing, it's not quite clear when it, before, during, or after the seizure. I know it says so in the text, but we could do some sort of timeline for it, like a dynamic animation timeline. What would you say about that? Also, can we add an explanation at the bottom? So keep the viewable height of the simulation window at, say, 80-90%. It wouldn't let me finish. It's a rude little robot. Like continuing from the previous request, can we do both? So can we make the viewable height of the simulation window at 80-90%? So then we can scroll to a text explanation of the simulation at the bottom of the page, and there we'll have an overview, details, how to use, what is it doing, and the relevant literature and stuff like that. Can you do that? I don't know if it can do both prompts. Can it do both prompts? So we had a tonic drop and has this swoosh sound. Master in normal. Yeah. Tonic. That doesn't work.
Okay, I can help you with that. The plan is to modify the page structure to constrain the simulation view to approximately 85% of the viewport height. Enable vertical scrolling on the page. Add a new section below the simulation area for textual content, including an overview, usage instructions, a brief explanation of the simulation, and links for further reading. Relocate the disclaimer to this new section. Here are the proposed changes. Index.html. The main changes involve removing